So we have this function, this new function of delta, and we can now try and look at this space a little bit. Okay, so we have to remember that because we minimize over the x here, we minimize them out. So the entire function L, which we wish to maximize, depends only on this new set of variables delta. And if we look at this, for example, we have here something that is linear in delta. So we have planes, and we have a few of them. You see, each solution x gives us a different plane. Every solution x corresponds to a different plane. And now we pick, for a given set of deltas, we pick the lowest of these. So this is, so these are planes in, let me call this delta space. And this is now a lower envelope of planes in delta space. And now we actually have a sum of these. So the lower envelopes, this is a concave function, and if we sum up lower envelopes, then this is still concave. And here we want to maximize this concave function. And maximizing a concave function is just as friendly as minimizing a convex function. Okay, this is a friendly problem. By the way, each individual plane just has a slope of 1. Yeah, I can multiply these deltas with a 1. So each individual plane has a slope of 1, but I'm actually adding up a few of them. So so the overall thing that I'm optimizing over in the end need not just have slopes of +1 or -1. So, you know what it looks like qualitatively is this. Here's my 1D sketch of delta space, and here I'm showing L of delta, and we want to maximize this function. And by the way, this, so now we have a convex set and we want to maximize it. This will remind you of a linear programming problem, and in fact it is. So this can be written as a linear programming problem. Excuse me. So here, for example, I am maximizing the minimum of In this case, I have drawn 6 planes. The minimum takes the lower envelope of these, and I can now introduce an auxiliary variable psi, and can say that I want to maximize over delta and over this auxiliary variable such that psi is always upper bounded by each of these planes. So in this case, 6 inequalities, and I can rewrite this in standard form like this. So I can concatenate my variables psi and delta and write it like this. So this is the standard form. Of an LP. And so what we see is that overall maximizing this lower bound or maximizing the dual amounts to solving an LP. Yes? Maximizing the lower bound amounts to solving an LP. And in the last hour we saw that I can also relax this primal formulation, also get an LP. So the difference is that this dual LP can be made to be, or can be chosen to be friendlier than the primal one. So the dual LP can be chosen to exploit the structure in the model. In other words, this means we choose a reparametrization that is a good fit for one of our hammers, and the hammers we have are max flow min cut or belief propagation on a tree-shaped graph, or other things we can do efficiently is finding shortest paths and such. And in the example above, I chose one particular reparametrization, namely where we really chopped up the graphical model into all its single units. So each unary term, each pairwise term became a separate graphical model. But actually you obtain better results if you choose different decompositions like trees, as I mentioned earlier. Yeah. The dual LP can be chosen to exploit the structure in the model. We choose a reparametrization that is a good fit for our hammers. So here essentially any polynomial time algorithm. So because we solve a relaxation, we lower bound the map solution, and this function, this Lagrangian, is a function that we want to maximize. Okay, now how do we maximize it? One possible approach is subgradient ascent. This is like gradient descent, but for non-differentiable objectives. Because you saw that we have these kinks in this function L that we want to optimize. And if we have, if we are, let's say, at this point, and this is again delta space here, and this is L of delta, and the lower bound over which we want to optimize is this one. The lower envelope over which we want to optimize is the thick black line. Then if we start at this point, it's pretty clear the gradient, or if I put a tangent, it goes here. But if I'm at this point, I have a choice of how I define my tangent. It could go here, or there, or there, or there. Yeah? So it can lie anywhere in this cone or in this wedge spanned by the planes. And these are, so collectively, these are called the subgradients of my function at the point where the derivative is discontinuous. So, yeah?
Sorry, but I'm a little confused. So what do we need to maximize now? Do we already have our linear
we want to walk up the, so the thick black line is this function L of delta, which has its maximum somewhere. And initially, we start with our original parameterization. So initially, before we start moving potentials around, all deltas are 0. So we're at this point. And now we want to walk up this function. So indeed, we can start by initializing our search at delta equals 0. And then we solve in each of our subproblems, solve for the optimal labels. So xit star means it's the optimum label at node I in the teeth part of my decomposition. Star means it's optimal, given the current delta, which is 0, meaning we solve all our sub-problems independently.
So this is what we are doing with the linear optimization.
So I'm trying to solve this linear programming problem. I could just use an LP solver. However, I have rather many dimensions, and instead of using the standard LP solver, I'm trying to better exploit my hammer, and this is why I'm here using a different method, because it's difficult to tell an LP solver about, the LP solver is a black box and it's difficult to tell it about the structure in our problem. So this is why we don't invoke the standard LP solver here, but do something different. So by fixing the delta and by optimizing over the labels. So the solving for optimal labels can, for example, if I have decomposed my entire graphical model into a sum of trees, then this solution can happen, for example, with belief propagation, BP. Because then I know that I do in fact get the exact solution for every subproblem, however they don't match yet. Yeah? So now I want to make them match. And once I've found this optimum solution, we then have this function L of delta. Oh, it's XIT star and XIS star here. Okay. So I've now inserted my optimum solution, which means I'm now, I started initially at delta equals 0. So I started at the point that I'm painting now in blue. And I now have my current function L of delta, which currently is just this plane here. And well, I'm now walking up this plane. So to do so, I compute the subgradient. And to compute the subgradient, so I take the derivative of L with respect to, for example, delta ji, and delta ji is a vector. It has one entry for each state that my random variables can take. So I I could also write it explicitly as delta ji of state 1 and the derivative of delta ji with respect to state, I don't know what the last state is, L. Okay, so this is a vector. And, well, if you now take the derivative of this function L, you see that the first term here does not depend on this delta ij. The second term enters with a prefactor of 1. This term does not enter. This term enters with a prefactor of 1, and this term does not enter. Okay, I'm now taking the derivative with respect to ji, delta ji. So I have here a minus 1 and a plus 1 that as contributions. And these minus 1 and plus 1 as contributions are manifested here. So my vector here is 0, except for a minus I at the location of xis star, and then more zeros, and then a plus 1 at the location of the xit star. Did I get the signs right? Yes. And then more zeros. So what we see is that if xis star equals xit star, then the contributions to the subgradient cancel. So my labeling then already agrees, and there is no need to shift around any potential. But otherwise, if they disagree, we have this. And so now I have my gradient. I know in which direction to walk. And I only need to decide. So I found that I want to walk here to the right in delta space. But now I need to decide how far I want to walk. And the simplest way is to choose some magic step size. So delta new equals delta old minus alpha, the magic step size, times this vector that we have just written down, the subgradient. Or this was one component for the subgradient, namely for the component here, delta ji. Okay, so this thing here, this update of the dual variables, the picture that I've drawn last hour somewhere, let me look for it. The picture that I've been drawing here is a graphical depiction of what's happening in this update step. So I had a disagreement between my optimum labelings, and then I made the one potential smaller and the other potential larger. So now I have changed my decomposition my graphical models have changed. And now that they have changed, I can resolve for the optimum labelings. So if I did decompose into trees, then I still have the same decomposition into trees. They have the same structure as before, but the potentials on those trees have changed. So now I go back to this step 2. So go to 2. Go ahead. 2 is there. Okay, and then there are many choices for how exactly do you choose the step size, and there are fancier schemes, but this is how you can proceed in principle. And what we have done differently from the standard LP solver is that in step 2, we use our clever algorithm. We use our hammer, we use the algorithm for which we have designed our decomposition. And this is something a standard LP solver as a black box cannot be so easily made to use. Okay, now this has its limitations, of course. For example, if you have a function, I'm drawing some equicontour lines. Let's say this is delta 1, and this is delta 2. I'm drawing some equicontour lines here. If I am at, so let's say I optimize one variable after the other. I start here. I first walk to this point because I started at 0. So I walk up a little to this point, and now unfortunately my objective increases both with respect to this variable and with respect to that variable. So if I try to optimize with respect to just the one or just the other variable, it looks like I am done already, yeah, because I'm sitting just here at this cusp. So what I need to do is I really need to optimize with respect to two variables simultaneously, and this is called a block coordinate ascent, where block means we take a whole block of variables rather than just one at a time. And so that means we want to have subproblems where we optimize over many dual variables simultaneously. So where we optimize over many random variables simultaneously so that we can optimize many dual variables simultaneously. And one popular decomposition I have already alluded to. So if we have an MRF with horizontal and vertical pairwise terms, then this can, for example, be decomposed into just the horizontal and the vertical contributions. And then we can use dynamic program on each of these super simple graphical models to obtain the exact solution on each of these simple models. Unfortunately, they disagree, and then we start shifting around mass between the potentials to make them agree. And this is at the heart of methods like tree-reweighted belief propagation. So here I've used just single lines, which is a special case of a tree. You can also use trees. You could also use, that would be a tree, for example, that would be a tree. Okay. So we are we're running out of time, so I'm going to show you the last part just on the screen here. And you can read up on this in, there is a paper by David Sontag, or actually the material here is from the appendix of his thesis. So it's a PhD thesis from, I believe, the Courant Institute from 2010. It's available online. And this is in the appendix of his thesis. So we looked today at the primal relaxation and at this dual formulation. And if we use this particular dual formulation, and there are many possible decompositions, then the two relaxations are equivalent. So let's start here with the relaxation that we saw at the beginning of the last hour. So the set K are a relaxation of the integrality constraints. This was the primal LP relaxation. And these consistency conditions, which are here circled in green, can now be added to the objective function and multiplied with Lagrange multipliers. So what you see here is the objective function from above. But these constraints circled in green have now been added to the objective function using Lagrange multipliers. So you see we have for each of these constraints we introduce a Lagrange multiplier delta. Now we want to minimize with regard to the original variables and maximize with regard to the Lagrange multipliers. And we can now collect so we can collect terms. And you see, for example, that here we multiply delta with mu, and up there we already had a mu. So we can collect these terms and have mu multiplied with the psi minus all of these deltas. And after collecting all of these terms, we get something, we still have these constraints that the mu's should be non-negative and should sum up to 1. So it means our mu's are confined to live on the simplex, but we have a linear constraint, or linear objective function. So we want to minimize a function, that an objective that is linear in mu, but we restrict ourselves to living on this simplex. So we know that the solution must be in a corner of the simplex, and these constraints can thus be omitted, and instead of all of these constraints we simply ask, will we end up in this corner or in that corner or in that corner? So here the minimization over mu is replaced by a minimization over the label. And this is the exact, so the last equation is exactly the optimization problem that we saw before. Okay, so what do we want to remember here? The upshot is that the primal relaxation that we studied at the beginning of today, LP of psi, has the same, or is equivalent to this. It gives us the same energy as this dual LP. If we choose the specific decomposition shown here. So the specific decomposition was this one here, into so that we get a separate replica problem for every unary and every pairwise term. And as I said, there are many other decompositions possible. And in geometry, in terms of geometry, what this means is that we have, on the one hand, in the space of our variables mu, we had defined an energy, and the mu, really, we have some integrality constraint, and the map solution will give us one of these integral solutions. So maybe the map solution or the marginal polytope will perhaps look like this. So this would be the marginal polytope. Then we have a relaxation of this, the local polytope. And now we have a second space. So I'm drawing a second set of coordinate axes here. We have this dual space with its dual variables delta, and with this function, with this Lagrangian that we want to maximize. And so this was the function L of delta. And in this, for the particular decomposition that we chose here, there is actually there is no space between the red and the blue line. Yeah? So the duality gap for this particular decomposition is 0. For others, it is not 0. If it is 0, then it means by solving the dual LP, we have also solved the primal LP. However, it does not yet guarantee that we also have solved the original map problem. And in cases where this duality gap is non-zero, people try to shrink the duality gap in an iterative fashion by introducing new random variables. So by adding further Lagrange multipliers. Okay, we can think of this as a this was the current L of delta, which was already, or the current space, the current decomposition was already optimal in the sense that we had no duality gap. But if we do have a duality gap, then we can introduce new dimensions. Now this gets really hard to draw, and I'm sorry. Let's say this is the original L of delta that we find, and we can now, so this was the old delta, and we can now add new dimensions. I've tried to put these in the third dimension, and in this third dimension we may find that along this third dimension we eventually reach a point where we obtain an even higher value for our Lagrangian, such that we may eventually be able to close this duality gap, and we know that we have closed it when we have consistent assignments amongst all our random variables. And when we have a consistent assignment, then, by the way, we have reached a plateau of our function L, because in that case, if you think of the Lagrange multiplier formulation, if the constraints are fulfilled, then the Lagrange multipliers can take any values they like without changing the objective function. Right? In the Lagrange formulation with the Lagrange multiplier multiplying the constraint equation, and if it is fulfilled, then the whole product becomes zero regardless of the choice of Lagrange multiplier. So this is why in that case we have a plateau in our Lagrangian. Okay, so we have now surveyed quite a few methods for optimizing discrete Markov random fields. I may add one or two heuristic approaches next week, but other than that, I think we'll now move on to continuous MRFs and afterwards to neural networks.